Hello and welcome to a review unit or review section on rational functions. This is something you should have already covered, so a lot of this should hopefully be just review. And just in case it's not, hopefully it comes back to you really quickly in case you don't remember some if not a lot of this. And as you know, and as we already talked about, a rational function can be addressed as a fraction, a function with a fraction, specifically with variables in your numerator and or your denominator. So when we have this, for instance, we have this function 2x squared plus 4x minus 6 all over x squared minus 9. A couple things can happen. There are 5 things that we should be able to identify strictly from using an algebraic function. Now, from a graph, we could typically identify what a whole, vertical asymptote, x-intercept, y-intercept, and horizontal asymptote is. But from a function, you should be able to evaluate what those things are as well. So the first thing you typically should do is to simplify the function if possible. And that's where factoring kicks in. There's multiple ways of factoring that we need to recall, and the first one and the most common one, the first thing you should do is you should always look for a GCF. So in this first particular term, we see the numerator anyway, we see all of this can be, is all divisible by 2, right? So that means we have a GCF of 2. And if we divide out a 2 from that particular numerator, we end up with 2 times the quantity of x squared plus 2x minus 3. Okay, and we could look at this as well and say, hey, I think we could factor this some more. It's a trinomial. There aren't many factors of -3. In fact, it's just 3 and 1, where you change one of the signs. And you should get x plus 3 and x minus 1 to get the positive 2x. Okay, so the numerator can be factored completely. And then the factored numerator would have the GCF of 2 times x plus 3 and x minus 1 as other factors. Now, x squared minus 9 can also be factored. It is a difference of squares. Even though you have 2 terms there, typically we have 3 for a trinomial, but if we have 2, we tend to look for a difference of squares. And in this particular case, it is a difference of squares. X squared can be square rooted, 9 can be square rooted, and the difference meaning minus. So x squared minus 9 can be factored to, sorry, that was all one step, x squared plus 3 and x minus 3. So, in order to find a whole, after it's already completely factored, we want to know that it occurs when a graph or a function, it occurs in a graph or function when factors with variables cancel out. So what this means is, once this is completely factored, I notice that I have x plus 3 and x minus 3 in my numerator and denominator. And those could be canceled out, just kind of like how simplifying is. We are simplifying the function to a simpler term. So we could actually rewrite this to x minus 1, 2 times x minus 1 and x minus 3, okay? And when we do this, the x plus 3's cancel out, but that actually, we can't ignore them, right? They can't just disappear from the function. They have to be addressed. That means when we cancel things out, it creates a whole. So we want to take that x plus 3, set it equal to 0, and then solve. Minus 3, x is equal to -3, and there will be a whole at x is equal to -3, wherever that is on the function, and you'll see what I mean. Now, what I mean by this also is when it occurs when a graph or functions, when the factors cancel out, we have a different function. Let's call this g of x. And if I have g of x is equal to 3x times the quantity of x minus 1 and x times the quantity of x plus 2, this is already in its factored form, which is really, really nice. But if you notice, x's can cancel out here, and we could say x is equal to 0 there will be a whole. Okay, and here's what I mean. I'm going to pull up decimals. I already kind of graphed these for us, so we don't have to worry too much about typing these in. And here we have it. in red, there's our original function, 2x squared minus 4x minus 6. We GCF'd it out. We have the x squared minus 9 also factored out. And we can't actually see the whole on decimals. But as we stated, at -3, sorry, this should be f of -3. We could see that it is undefined. It will calculate it for us. You physically cannot see the whole on this particular graph because it is so, how would I say it? It is so finely tuned to all the values of it that it would be so minimal that you cannot see it. So at -3, it is undefined. That is, I'm sorry, that's not where the whole is. That is where, what canceled out? I forgot already. Was it 1? Let's check. Yeah, x minus 3. Oh, I wrote this wrong. Let's change it. 2x squared plus 4x. Let's change that in decimals. 2x squared plus 4x. That's supposed to be a plus. There you go. And this is still undefined. Okay. F of -3, it is undefined, and that's why I was wondering why there was an asymptote there. If I try to evaluate it specifically at 3, you could literally see that, hey, the function's, it looks like it's continuous. But if I plot it in that split second that I'm actually on it, you could see that it's undefined. So we have an undefined point. We would typically put an open circle there. Okay. So we want here, if there's a hole, there should be an open circle on the graph. All right. And then if you have g of x is equal to 3x and all this, the x's will cancel out. We could do the same thing. Here's the actual graph, and it looks like I actually messed this one up as well. So x minus 1, x plus 2. Ultimately, that's not going to matter in this particular one. But let's fix it. Let's actually show it. There's the function. If I change this to g of 0, because they cancel out at 0, you can see it's undefined here as well. It looks like it's there in our graph. And even if I zoom in all the way, it looks like it's there. But if I try to calculate it, you can see for that split second that I could get it, there you go, undefined. Okay? Now, going back to our lesson. Vertical asymptotes occur when a simplified function's denominator is equal to 0. So we already simplified it here in red, in this top right here. And we could say f of x, the denominator anyway. Let's say f of x is denominator. The simplified version of it is now x minus 3. And we set that equal to 0. So if we add 3, we get x is equal to 3, meaning we have a vertical asymptote at x is equal to 3. And when we graphed it, we could actually see that. Not the first one that I pointed out, but when I actually, not this one, not this one in blue, but this red one. Zoom back out. At x is equal to 3, you could see that there's pretty much that vertical line that doesn't get crossed between these two huge red curves are the function. Okay, vertical asymptote is occurring there. Horizontal asymptote we'll cover in a quick second, but let's talk about the x and y-intercept. X-intercept occurs when the y value is equal to 0. And in a rational function, that could only occur if the numerator is equal to 0. For instance, if I have 1 over 2, this could never be equal to 0. If I have 1 over 100, this is not, it's close to 0, but it's not it. 1 over a million, 1 over a trillion, it doesn't matter because 1 over something is a non-zero value. So even if I have 1 over x, x could be pretty much any number besides 0, but it would still be a non-zero value. So if you have a constant in your numerator, then there's no x-intercept. So here's a little start here. If there is a constant in the numerator, there's no x-intercept. And it's only a constant, I should say. If there's like an x minus 1, technically those could, I mean, we'll talk about it a little bit. And there is no x-intercept. We'll talk about it. But in this particular case, we have 2 times x minus 1 in our numerator. So in this particular case, 2 times x minus 1 is in our numerator. We're going to set this all equal to 0. We're going to divide this by 2 because it's outside the parentheses. We get x minus 1 is equal to 0. Add 1, add 1. We get x then equal to 1, which means we have an x-intercept at 1. So that means we're going to have 1, 0 be a point for our x-intercept. Okay? For the sake of it, I'm going to show the y-intercept as well. The y-intercept occurs when x is equal to 0, so all we have to do is substitute x into the function, and we could use a simplified function for this. So we have 2 times the quantity of x minus 1, 2 times the quantity of x minus 1 all over x minus 3, and we do this for x is equal to 0. So anywhere you see an x, you plug it in, you plug 0 in, 2 times 0 minus 1 all over 0 minus 3. So we end up getting 2 times the negative 1, because 0 minus 1 is negative 1, 0 minus 3 is a negative 3. We end up with negative 2 over negative 3, which is equal to 2/3. Okay, so that means our x value is 0, our y value is 2/3. This is our y-intercept. Okay, and we're going to look for these 2 points on our graph. 1, 0, and 0, 2/3. Well, looking at our graph, we could see our x-intercept at 1, 0 right there. Perfect. And at 0.66667, or 2/3. So we could see that it works. Okay? So those are your x and y intercepts. Those should hopefully be a quick recall how to actually evaluate it. The horizontal asymptote is the weird one, the tricky one, because there are in fact 3 scenarios that we need to know. And a lot of it has to do with just understanding how variables affect the numerator and denominator and their degrees. So we have to look at the degrees of the numerator and denominator. If the numerator degree is less than the denominator degree, then we consider this bottom heavy, meaning there's a higher degree in the denominator. Okay, it would look something like this. There's a constant in the numerator, there's a variable in the denominator, and when you have this, you kind of get this concept of 1 over 1, or 1 over 10, or 1 over 1,000, or 1 over infinity. 1 over infinity is a really, really, really small number. So as we progress through the numbers to the right, it actually gets really close to 0, but it never actually intersects with 0. As we said, if the constant in the numerator, if there's a constant in the numerator, then it can never be equal to 0. Okay? If there's a value like x minus 1 in the numerator, then you could put x is equal to 1 in your numerator. If x was equal to 1, then the numerator would be a 0 value. Okay? But here we have a constant in the numerator that could never be equal to 1, or never be equal to 0. But this number gets really, really close to 0, meaning the further right we go, the further it gets closer to 0. This just means our horizontal asymptote is going to be equal to 0. Okay? That's it. If it is a bottom-heavy equation, then the horizontal asymptote is equal to 0. The second scenario that we need to know is if they are actually equal to each other. If the degree of the numerator is equal to the degree of the denominator, this is a balance. And in this particular case, like we just had, we see the degree here is 1 degree here is also 1. So this is a balanced function. It's kind of like considering this. What if I rewrote this? What if x was equal to infinity? Then we would have 2 times infinity minus 1 over infinity plus 3. Well, infinity plus 1 is infinity. And infinity minus 1 is infinity. And infinity plus 3 is also infinity. And these kind of just infinity divided by infinities, they kind of cancel out. It's almost irrelevant to what happens. What's important, though, is what the coefficients are in this. So what is the coefficients of the numerator? What's the coefficient of the denominator? And this will make your horizontal asymptote. The coefficients of the highest degrees will be the horizontal asymptote. So in this particular case, we have 2 over 1. Okay? And you could actually see it in our graph. Sorry, I keep referencing it. It's important for us to see this on a graph, and I highly recommend using it on Desmos to just kind of visualize a lot of this. At 2, we could see that horizontal line what we put a dotted line across y is equal to 2. Okay, and I forgot to put that here. Horizontal asymptote is y is equal to 0, so we would put y is equal to 0. Here we would do y is equal to 2. All right, last one. If it's not less than or equal to, it would be greater than. If the numerator is greater than the denominator in terms of degrees, we call this top-heavy. And if it is top-heavy, then there is no horizontal asymptote. Okay, we'll actually have a slanted asymptote. We're not going to worry too much about that. That's not going to be terribly important for what we need for moving on the limits. But those are the 3 scenarios that we need to know. Okay, these are the 5 things we need to be able to do if you are given a particular function. What's the hole? If there's a hole. Okay, so we have to simplify the function if we can, factor it, GCF it, whatever you need to do to simplify it as much as we can. Determine holes if things cancel out. Is there a vertical asymptote? What are the x and y intercepts? What is the horizontal asymptote, if there is one? And then those are the 5 things you should be able to do. So, quick practice. Going back into that packet that we gave out, we have these particular functions that we need to be able to work through. Okay? First and foremost, is there a hole? Is there anything canceling out? In this particular case, no, because this is x plus 3, this is x minus 4. You can't cancel out the x's. So is there a hole? None. Vertical asymptote, where the denominator is equal to 0. So we do x minus 4 is equal to 0. We add 4, x then equal to 4. So the horizontal asymptote there. Okay? I'm sorry, vertical asymptote. Oopsies. Vertical asymptote at x is equal to 4. All right. Horizontal asymptote. Look at the degrees. They are equal to each other. That means this is balanced. The coefficients are 1 and 1. So horizontal asymptote occurs at 1. Y is equal to 1. Okay. X-intercept occurs when the y value is equal to 0. So we could say this one's balanced. Or when the y value is equal to 0, meaning the numerator is equal to 0. Here we have x plus 3 in our numerator. We set that equal to 0. Subtract 3. We get x is equal to negative 3. So our x-intercept is going to be negative 3 comma 0. This 0 is coming from here because in order for it to be an x-intercept, the y value has to be 0. Last but not least, y-intercept is when x is equal to 0. And all we have to do is substitute x in for 0. So we get 0 plus 3 over 0 minus 4, which is equal to negative 3/4. So we get a value 0 comma negative 3/4. And now we could actually plot a lot of this out. We have a hole, none, no hole, vertical asymptote at 4. We're going to have a horizontal asymptote at 1. And then we are going to have x-intercepts at -3, 0, and then 1 at 0, -3/4. And with this, we should hopefully kind of identify, we should have something like this. And we'll have one on the opposite end too. This usually is what happens when you have a balanced equation. Well, we'll get into a lot of this nitty-gritty stuff and behavior and behavior at asymptotes later. Actually, in this particular case, if this was, let's say, 5, this would be positive over positive. Yeah, that's fine. And then let's go to the next one. All right, let's factor this. We could factor out a GCF of 2. So we have x plus 2, difference of squares in the denominator. So we're going to have x plus 2, x minus 2. These cancel out, which means we have a whole at x plus 2 is equal to 0. Subtract 2. X is equal to -2. Whole at x is equal to -2. Okay, vertical asymptote occurs once again, hopefully if you want to use this little kind of key to do this, where the denominator is equal to 0 in the most simplified form. So if we simplified this completely, this would be 2 over x minus 2. So denominator is equal to 0 is that x minus 2 is equal to 0. Add 2. And then we get x is equal to 2. Horizontal asymptote occurs in this particular case. This one is a bottom-heavy equation. Degree is 1, degree is 2. So that means the horizontal asymptote is 0. X-intercept occurs when the numerator is equal to 0, and we're looking at our simplified version of this. That's impossible because we have a constant, so there's none. And then y-intercept, where x is equal to 0, we end up getting 2 over 0 minus 2, which is equal to 2 over -2, which is equal to -1. So we have 0, -1. Then we graph this. We have our vertical asymptote at -2. I'm sorry, +2. And I should be using red. Then we have our horizontal asymptote at 0. Okay. We also have no x-intercept, but a y-intercept at 0, -1. We also have a whole at x is equal to -2. So when we actually graph this, it's going to be something like this. We're going to have a hole here. So put a big circle there. In my case, I'm going to have to erase a little bit to show the hole. And that's how you should demonstrate it. Okay? And then if you want to understand end behavior really, really quickly, if I chose any value here, like for instance 3, what will it be? Well, 2 times 3 is 6. 6 plus 4, that's a positive number. And then 3 squared is 9. 9 minus 4 is also a positive number. So we're actually going to get something like this. Okay? So it's kind of understanding how some values are going to just be positive or negative where you want it to be. All right. I will leave these two up to you to try out, and then I'll post the answers to these online. All right. Hopefully this was easy and a quick recall, and I will see you in the next one. Bye.